Many times you'll read a paper and a solution will be presented that's quite elegant and proven to be optimal in some way, and it's based on a bunch of quantities that you may not know. Well, we have that problem here. The Wiener solution is based on expected values, and we may not have the expected values. In fact, it's very uncommon. So if you're reading a paper that has something like that, the first thing to do is to start looking at those quantities and say, can we estimate them, and what impact will estimation have? Well, we can also use estimates in this case, and we're going to estimate our correlation matrix just using samples of our vector y, and the cross correlation once again with samples of y and d. Now, if we have complex, that transpose turns into Hermitian transpose, or complex conjugate transpose. And in the second case, for complex systems, the complex conjugation goes on D, like so. So, once we've got all that, we end up with Ry hat H is equal to Ryd hat. Guess we can make that H bold as it's a vector. Now, you might notice a few things that are perhaps different from the way we usually do things. When we're estimating a mean or a variance or something, we usually have a 1 over, in this case it would be m plus 1, out front. But since these quantities appear on both sides, we can just effectively ignore the normalization as it cancels out. If we're going to do that, then our limits don't matter as long as they're the same on both Ry and Ryd. And if we're computing this in some computer system, as we would likely do, it's very likely that we're going to be using the same number of samples of y to compute both Ry and Ryd.